Dear students, we now discuss the topic diagonalization of a matrix. A square matrix A of order n is said to be diagonalizable if it is similar to a diagonal matrix. That is, for an n by n matrix A, the matrix D equal to x inverse Ax is diagonal with the eigenvalues of A as the entries on the main diagonal. Also, X is the matrix with these eigenvectors are column vectors. So, for an n by n matrix A, the diagonal matrix D is a matrix in which the eigenvalues are the main diagonal entries. So, for constructing a diagonal matrix, first we find the eigenvalues and eigenvectors of the matrix, and then we form a new matrix X with the column vectors are the eigenvectors. Then you take x inverse Ax. The product is the diagonal matrix D. The working rule for finding the diagonal matrix of a matrix is: first you find the eigenvalues and eigenvectors. Form the model matrix X with the column vectors are eigenvectors. Find the inverse of the model matrix X as x inverse. Then form the product x inverse Ax, and that matrix is the diagonal matrix D. Then the diagonal matrix has the diagonal entries are eigenvalues. For example, we consider the matrix 2, 4, 4, 2, and we are now going to diagonalize this matrix 2, 4, 4, 2. That is, we form a diagonal matrix with the diagonal entries are the eigenvalues of this matrix. We have take the matrix A as 2, 4, 4, 2. Then for finding the eigenvalues, we take the characteristic equation. So the characteristic equation is determinant A minus lambda I equal to 0. That is, we have 2 minus lambda, 4, 4, 2 minus lambda, determinant equal to 0. Take the product diagonal wise, it is 2 minus lambda, and 2 minus lambda is 2 minus lambda the whole square, minus 4 into 4 is minus 16 equal to 0. Expand, we have a lambda square minus 4 lambda minus 12 equal to 0. Solving this quadratic equation, we have a lambda minus 6 into lambda plus 2 equal to 0, and the values of lambda are 6 and minus 2. So the eigenvalues are 6 and minus 2. So for diagonalizing this matrix, now we find the eigenvectors for these eigenvalues 6 and minus 2. So first we find the eigenvalues for lambda equal to 6. For lambda equal to 6, we substituting here, we have 2 minus 6 is minus 4, then 4, then 4, 2 minus 6 is again minus 4. That is, there exists only one equation, minus 4x1 plus 4x2 is equal to 0. So from that equation, we have x1 equal to x2. So the eigenvector is x1, x2 transpose equal to 1, 1 transpose. Now we calculate the eigenvector for lambda equal to minus 2. Then we substituting the value of lambda equal to minus 2 in the characteristic matrix A minus lambda I. We got 4x1 plus 4x2 is equal to 0. That is, x1 equal to minus x2. We have the eigenvector x1, x2 is equal to minus 1, 1. Take x2 is equal to 1, we have x1 is equal to minus 1. So the eigenvector for lambda equal to 6 is 1, 1, and eigenvector for lambda equal to minus 2 is minus 1, 1. Then for diagonalizing, we form the model matrix X as x is equal to, we write the column vectors are the eigenvectors. Here First write the first column as the eigenvector for lambda equal to -2, that is -1 1. -1 1 is the eigenvector for lambda equal to -2, that we put in the first column, and the eigenvector for lambda equal to 6 is 1 1, and then we put in the second column. Okay, so we form the model matrix X in which the column vectors are the eigenvectors. Now for diagonalizing, first we have to find the inverse of that matrix X. The inverse of the matrix X is X inverse is equal to 1 by determinant of X into adjoint of X. But adjoint of X is cofactor transpose or transpose of the cofactor matrix. So here we have the determinant of this matrix is -1, -1 it is -2. So 1 by determinant 1 by -2 into then cofactor for this matrix X is we have for a 2 by 2 matrix, the cofactors are we interchange the main diagonal entries and put a minus in the sub diagonal entries. That is we have a 1 -1 and put a -1 in the sub diagonal entries. We have -1 -1 and you take the transpose of this cofactor. So the inverse of a matrix is the transpose of the cofactor matrix by determinant of the matrix. The determinant is -2 and this is the cofactor matrix, and you take the transpose. We have a 1 by 2 into -1 1 1 1. That is here we multiply this minus in the matrix. So this is the inverse of this matrix, that is 1 by 2 into -1 1 1 1. Then for diagonalizing, you take the product X inverse Ax. That is 1 by 2 into -1 1 1 1 is the inverse, and we have the given matrix A is 2 4 4 2 and X is -1 1 1 1. Then you take the product. We have that equal to 1 by 2 into this matrix is -1 1 1 1. You take the product of the last two matrices. We have the product is 2 into -1 -2 plus 4 into 1 is 2. So it is 2. 2 into 1 2 plus 4 into 1 is 4. 2 plus 4 is 6. 4 into -1 is -4 plus 2, that is -2. 4 into 1 is 4 plus 2 into 1 is 2. 4 plus 2 is 6. Then again you take the product. We have a 1 by 2 into -1 to 2 is -2 -2, that is -4. -1 into 6 is -6 plus 1 into 6 is 6. So -6 plus 6 is 0. 1 into 2 is 2 plus 1 into -2 is -2. 2 minus 2 is 0. 1 into 6 is 6 plus 1 into 6 is 6. 6 plus 6 equal to 12. And dividing these two, we have the matrix is -2 0 0 6. And this is the diagonal matrix with the diagonal entries are our eigenvalues -2 and 6. Okay, so in the model matrix X, we take -1 1 as the first column vector, and this is the eigenvector corresponding to -2. So here there is -2 as the first entry, and 1 1 as the eigenvector corresponding to lambda equal to 6, corresponding to the eigenvalue 6. So 6 is in the next diagonal entry. Okay, this is the procedure for constructing a diagonal matrix or diagonalizing a matrix. The condition for diagonalizing a matrix is we have if the eigenvalues are distinct eigenvalues, the matrix is diagonalizable. The another condition is if the eigenvalues are same and the eigenvectors are linearly independent, then also the matrix is diagonalizable. Here the eigenvalues are -2 and 6. They are distinct eigenvalues. So the matrix is a diagonalized matrix, and the diagonalized form of this matrix is -2 0 0 6.